work that has been supported by NSF, long foundation, Simon Foundation, Institute for Math Studies, and many others. And this book from about a year ago, a book on author of a book on variety, general varieties, which sets out the theory for stable varieties. So happy to have you today. Talk about.
Can you deform a plane to a settled surface? Thank you very much. Thank you for the invitation. So there's a lot to talk about this. So I probably will not get to everything interesting, but hopefully I will still tell you something interesting. So I guess maybe one question is, what exactly is a saddle surface? You probably know it, but let me start with that. So one possible way. So what's a saddle surface? So it's a surface where in one direction it curves this way, and then other direction it curves that way. And so it looks like a saddle. So one possibility in, say, R3, you can look at the graph of the equation x squared minus y squared. You know, in the x direction, the parabola goes this way, the y direction the other way, or I probably said it the opposite way than it actually is, but think of me standing on my head, and then it would work. Okay, so if the question is, can you deform a plane into the graph of this? The answer is, of course, because if you have a graph of a function of two variables can always be deformed, right? There's the projection, and if you do the projection, so I'm not going to try to draw this correctly, but you know, you have a graph over a plane, then there's a way you can squish that down. So that just tells you that the question in this case is not that interesting. So let's do slightly different. So first of all, I'd like to generalize this to arbitrary fields. So when I take this equation, this makes sense in any field. So I can replace, you know, you can replace R with Q or C or basically any field. Or if you're so interested for this particular equation, you only need a ring. You don't even need to be able to divide. But definitely these work, and I will concentrate on the complex case. And actually, right, let me backtrack slightly if I can get this to move. So I was saying deform, but in this case, these are actually isomorphic. The projection gives an isomorphism. So if I like to think of these surfaces abstractly. So I may give you an equation, but when I ask if it can be deformed, I don't necessarily mean that in that particular situation, it doesn't have to stay within there. In this case, it does work there, but more generally, we're interested in the isomorphism classes of these. So again, I can change the field, but the fact that this is a graph will not change. So again, there's nothing interesting there. But a more interesting question is, what if we go to a projective case? So let's say, so what does that mean? I would like to embed this into a projective space. So let me recall what that is. So the representation that I like about projective space is that you add one variable and you say, well, not all of them, not all xi0, and also so these xi are from your base field, let's say from C, and then you mod by an equivalence relation where you say that two of these are equivalent if you multiply by a non-zero constant. Okay. And in here, so this Pn contains a subset where I choose x0 to be not zero. And this can be identified via this equivalence relation with those whose coordinates are essentially the same thing. But if x0 is not zero, then I can divide everything by x0. And that via this will be an equivalent representation. But now here, I don't need to do anything else because it's not all zero because this is one. And also, I kind of killed the equivalence by determining or insisting that this is one. So there's no other requirement than this is in the field. So this can be identified with Cn, or if you, as we like to call that, An for affine space. If you're not big on the difference, don't worry about it. One reason to use the letter is that Cn suggests that it's a vector space, so there's a distinguished point. We don't want to do that. So if you forget that, then it becomes An. Also, it keeps out the riffraff that we're speaking a secret language. Call it an affine space. Okay, so that's our projective space. And the point is that you can think of this, so Pn is a compactification of Cn. So I like to think of the projective space as something that extends the affine space, or you can think of things go out to infinity and you add points at infinity. I'm pretty sure most of you or all of you already know this, so it's mainly for me, but I also want to establish some notation. So another thing that we'll need is that in Pn, I can look at hyperplanes. If I have a hyperplane, that's a linear subspace. So this is defined by, so this is the zero set of a linear, maybe I should say homogeneous linear equation. So in other words, this could be defined by something like A0 x0 plus An xn equals 0. So a hyperplane corresponds to something like the coefficients in this linear equation. And if you think about it, two such n tuples give me the same equation if I multiply them by a non-zero constant. Because if I multiply this with 2, it's the same coordinates that satisfy that. So I have that. And also, if I actually want an actual hyperplane, then some of these coefficients are better not be 0. So they're not all 0. So we have the same description for these coefficients as for Pn. So the hyperplanes form the dual projective space, where the points of this dual projective space parameterized by these coordinates correspond to, so the dual projective space that we denote by Pn dual, you can think of this, so this is abstractly isomorphic to Pn, but really the points correspond to hyperplanes. And then, for example, we can look at the product of these two. And in here, look at something like what one could call the universal hyperplane that consists of A0 An cross x0 xn, with the requirement that if I take there, it's almost like a dot product, then this is 0. Okay? And then if you take this guy inside this product and project it to the first vector, and for every hyperplane, the fiber is actually the points of that hyperplane. Is all right? And probably everyone knows this. Oh, I forgot. So there's a chance that some of you get bored. And I recently learned a puzzle that I'm going to share. So if you get bored, just work on this puzzle. So you got a grid of dots, 6 by 6. And the task is to draw a piecewise linear curve that has 10 segments and goes through all the points. So I show you one that doesn't work. So you could do this 3, 4, 5, 6, 7, 8, 9, 10. It misses one. So you have to do a little bit better. So back to the boring stuff. Okay, so okay, my high level electronic guy is not working. Okay, so we had that affine version that wasn't interesting, but I want to make it projective. So how do we do that? There's not going to be a reveal about that. It's not connected to the talk. If you're interested, I have a solution, but it's not going to come out of the talk. But it's kind of a neat thing. So I'm just saying this, that, you know, don't stay because you think that this is going to come out of the saddle surface. Although that would be really cool if someone could do that. So if I have that equation, z equals x squared minus y squared, this is inside you know, c cubed, which is inside p cubed. So this is a compactification. And you see the way we went here from projective coordinates to affine coordinates was to divide by one of the coordinates there. So to go backwards, that we imagined that we already did that and then work backwards. So let's say that here the coordinates are x, y, z, and t. That means that to get really this equation, I should have this. So now would like to have an equation that doesn't have fractions. So I multiply by t squared. So I get zt equals x squared minus y squared. And now this x squared minus y squared, as we know, can be written as x minus y times x plus y. And now if I do a very simple coordinate change, and I'm going to abuse the notation and write that this is the same thing as zt equals xy. Okay? So this is a much friendlier version. And you probably can't see it from there. These three lines a little bit darker white. This is really white. So these x and y are different than those x and y. Okay? So we have this equation. And now the question is, so I have this guy. This lives inside P3. And I can also think of, you know, I also have P2, which is the projectivization of the plane. And now the question is, can I deform this plane into that? Now, this is not that obvious because there's no longer a graph. So there's not such a simple relationship. So let's investigate this. So I want to understand this a little bit better. And here's a way to understand this more abstractly and not inside P3. So if I take P1, so if you want, this is actually a sphere, Riemann sphere with a complex structure. And I take P1 cross P1. I can define a very simple map to P3. And it goes like this. So let's say the coordinates are A, B, and C, D. And I map A, B, C, D to AC, AD, BC, BD. So I multiply each of these with each of these, not in the same coordinate. And now if I label these X, Y, Z, T, oh, okay, I didn't do it right. I should have done AC, BD. Sorry about that. AB, A, D. Now this is totally not visible from more than 2 meters. So AC, BD, AD, BC. I just changed the order. So you can see that these coordinates satisfy this equation. And it's relatively easy to see that everything that satisfies that equation can be written this way. So the image of this map is exactly that surface. So let's call the surface there Q for quadric. And you can actually, with a little bit of computation, you can prove that this map is 1-to-1. So essentially, we're identifying Q with P1 plus P1. In fact, so if you think of these as complex manifolds, then P1 cross P1 makes sense. But as algebraic varieties, P1 cross P1 doesn't make sense because it doesn't a priori have a representation as a zero set of some polynomial, but this is it. So this is how you can define P1 cross P1. So that this is really P1 cross P1. So now the question is, can I deform P1 cross P1 into P2? And again, the question is how, in what category do we mean it? But it turns out that it almost doesn't matter what category, because the answer is that we won't be able to do that. So why is that? So here's a little bit of computation, or here's a claim that if I take two curves in P2, by that, so this might be an algebraic geometer's point of view. If you prefer, take P2 as a complex manifold and take two compact Riemann surfaces, complex Riemann surfaces. So two compact one-dimensional complex submanifolds. So the claim is that then they intersect. Okay, so why is this? Well, so the reason for this is that if I have, so these are curves. So if I have a curve in P2, then it's defined by a single equation. So Ci is the zero set of some homogeneous polynomial in with complex coefficients. And there's something classical about finding, so we want to find common solutions of F1 and F2. There's something called the resultant of two polynomials. Has anyone heard of that? Okay, very good. So there's a polynomial that's the resultant of these two. And what it happens that this polynomial is a polynomial in the coefficients of F1 and F2. And the condition is that this polynomial has a root if and only if those two polynomials have a common root. And then we're working over complex numbers. If I have a polynomial over the complex numbers, then the fundamental theorem of algebra says that it has a root. So this guy will always have a root. And therefore, F1 and F2 will always have a common root, but that means that then the two curves meet. So great, we got this. But on P1 cross P1, so P1 cross P1 looks like this. And I can easily draw two curves here that do not meet. So now what does this mean? This means that you can actually think of the homology or cohomology class of these curves on these surfaces and their cup product. This says that any two one cycle on P2, if you take their cup product, it will be non-zero. And on P1 cross P1, the cup product will be a cup product of these two curves will be zero. So that means that their cohomology theory is different. So they're not even, you can ask if okay, sorry, I forgot where I was. So right now, what I want to conclude from this, so what this means is that Q is not homeomorphic to P2. So I'm not talking about deformation at the moment yet, just that topologically, these two complex manifolds are different. In particular, they're not diffeomorphic. So P2 and Q are not diffeomorphic. By that, I mean that if I think of them as smooth manifolds, not even complex manifolds, then they're not diffeomorphic. So that actually tells us that then as complex manifolds, they cannot be deformed into each other. So let me tell you why that is. So there's something called, where am I? Sorry, I have to catch up my notes too. So there's something called Ehresmann's theorem. And it says that if you have a proper submersion, then the fibers are diffeomorphic. Actually, it says more. It says that as if you think of this as a fibration of smooth manifolds, then it's locally trivial in the smooth manifold category. But this means that if I want to deform two complex manifolds as complex manifolds into each other, that means, and if they're compact, then that would mean that deformation would have to be a proper submersion in the as considered as differentiable manifolds. So only complex manifolds that are diffeomorphic can be deformed into each other. This might be something that you already know, so forgive me for that. There's the distraction for those who know. So corollary of this is that P2 cannot be deformed into P1 cross P1 or Q, whichever title you like, as complex compact manifolds. Okay. So next, I would like to tell you that, but they can be. Not as compact complex manifolds, but almost. So if we allow some simple singularities that which, if I get that far in Magi theory, we're forced to allow singularities, and we don't even have to go the full force. Almost kind of like the simplest type of singularities that we can imagine, then these two can be deformed into each other. And I think just this construction in itself is interesting. So even if you don't care about the modular consequences, then I think I like this construction. So I think this is interesting on its own. So if you've been working on this puzzle until now, this is a new entry point that you can start paying attention now. You're not going to lose anything. I mean, this is understandable on its own. So here's let's see. Let me actually start here. So I'll have this for longer. So here's a very general construction that an interesting deformation technique. It's the following. So let's suppose that I have a complex manifold in Pn. Now, okay, I successfully erased the definition of Pn that I wrote up there. But if you remember, we had n+1 coordinates. We mod it out by the multiplication by a non-zero coordinate. You can think of that as a map from one larger affine space minus the origin. And so if I have something projective, I can think of basically the same equations that define that projective submanifold, define a submanifold in the one larger dimensional affine space. So there's something that we call the cone of X, or just simply Cx. And it's really, I would like to think of this living in an+1 and stick that 0 into that, because that 0 will be in the closure. And in fact, I would like to embed this into one larger projective space and then take the closure of this cone there. So I would like to look at the projective cone here. So we have something like this one larger projective space. In there, we have this hyperplane at infinity, Pn. So hyperplane at infinity, which is isomorphic to Pn. And then in here, I have some submanifold X. I have the 0 that's outside here. And then I have this cone. Now, if you're wondering about these steps, if I take the complement of this plane at infinity, the complement of that is an+1. This is 0. So if I just take the cone, that's exactly all of this except that. But if I take the closure, then that exhibits this X as the intersection of this projective cone with the hyperplane at infinity. Okay, so that's one thing. And another hyperplane, I would like to take another hyperplane, which is, I can take a generic hyperplane inside this hyperplane. So something like this. And then take the cone over that, which will be actually a hyperplane in the bigger space that contains that point. And I'll call this H0 for a hyperplane intersecting or going through the 0 point. And then I can think of maybe I'll use the yellow thing. So I have this intersection with X. And so if I take this H0 hyperplane and intersect it with this cone, then I get the intersection of this hyperplane with the original X and the cone of that. So this guy here is this projective cone intersected with H0. So I have this projective cone, and I have two intersections by hyperplanes. Now, if I remember my original plan, then I would have what I wrote here earlier, namely we had this universal hyperplane in the product of the dual projective space and the and our projective space. And now, if I do this, let me see. I think I need this for actually n plus 1. But that hopefully doesn't bother anyone. So now if I have a, let's say I have an arbitrary, say, an compact sub-analytic space of Pn plus 1, or if you want a projective algebraic variety. And what I would like to do is think of this Z here, take its preimage in the product. So in other words, I take this and then intersect this guy with this guy. So what is that? So what's happening? I have the entire PM dual projective space. So if I pick a point here, which is, say, a hyperplane, now the fibers of this over that point are the points of the hyperplane. The points here are the points that map to Z in the projective, the original projective space. So if I intersect this with that, then I get exactly the points of the intersection of H and Z. Does that make sense? So I claim that H intersected with Pm plus 1 dual cross Z. If I think of this fibered over Pm plus 1 dual, and I pick H, let's say this fibration is pi, then pi inverse H in here, I can think of this. So if you want, you can just project this onto Pm plus 1, or that projection will be, so the fiber, so this lives in this product. So this fiber lives in a copy of Pm plus 1 over that point. So in that copy, this corresponds to the intersection of H, this hyperplane, and Z. Does this make sense? This is the most crucial construction of today. So tell me if you have questions. So basically what I'm doing is I look at this universal hyperplane, so all the hyperplanes in Pn, and I take something in Pm plus 1, I take something in Pm plus 1, and I pull it back and intersect it with this universal hyperplane, which means that for every single hyperplane, I intersect it with that hyperplane. So what I get, that this intersection, let's call this, say, curly Z. Now, if I look at it, so I have this curly Z maps to Pm plus 1 dual pi. Now, this is a family of these intersections. So the consequence of this is that if I have an arbitrary projective subvariety of a projective space, say this cone, then its hyperplane sections are deformations of each other. Even though technically within that projective space, they may intersect. So in that projective space, it's not a bona fide deformation, but with this kind of separating those hyperplanes gives me a family. So this is a family of hyperplane sections. So the consequence is that if I have a closed subvariety of Pm plus 1, then the hyperplane sections are deformation equivalent. Okay, so this is what I would like to use in our particular example. If I'm Right. So let's see. We already saw that P1 cross P1 can be embedded into P3 via this product multiplying the coordinates. There's also, P1 can be embedded into P2 by taking degree 2 polynomials of the coordinates. So I can do a squared, ab, b squared. And now, what if I combine these two? So let's say that I want to map P1 cross P1 to P5 by taking the following, AB cross CD. So in here, what we did was multiply A to C, A to B, B to C, B to D. But I want to do this first and then multiply with that. So this maps to A squared C, A squared, AB C, B squared C, A squared D, ABD, B squared D. You can count these are 6 coordinates. That's exactly P5. So this gives me a different embedding of this P1 cross P1. And in fact, the result is something classically known as a quartic rational. So scroll means a ruled surface where, ruled surface means a P1 bundle. The scroll means a P1 bundle embedded so that those P1s are actually lines. And, this P1 is embedded with linear coordinates, so that becomes fun. But this is not important at the moment. What's important is that this gives us a degree 4 surface. And now we discussed hyperplane sections. So if I intersect this with the hyperplane, so if H is a hyperplane in P5, then, okay, so I don't want to call everything P1 cross P1 because it's important where they're embedded. So let me call the image of this, say S is the image. So this S is isomorphic to P1 cross P1. But when I say S, I mean the one embedded into P5 this way. So the question is, what is this S intersect H? Now, this is something that this is given by coordinates, and hyperplane is given by a linear equation. You can actually compute. And I'll save you the trouble and tell you what this is. So this is actually, not surprisingly, a rational, I think I should have called this rational quartic scroll, but this is a rational quartic curve. If you're familiar with the twisted cubic, are you? Twisted cubic? This is the next step. This is the twisted quartic. So a rational quartic curve is so this H is P4. So the twisted cubic lives in P3, and it's given by the degree 3 polynomials. If you do that in one higher degree in one or more coordinates, then you get the twisted quartic. And this exists for every degree. And the theorem says that if you have a rational curve of degree D in PD, it's actually necessary this. There's only one abstractly that any two such embeddings can be deformed by a projective transformation. So this is actually something we know very well. So if you want, this is the image of t to the 4th t cubed u t squared u squared t u cubed u to the 4th. Okay, great. So we have that. Now I want to do something similar for P2. Okay. So this is an hour, right? The talk. Okay. So how can we do something similar for P2? So I want to take P2 and embed it into P5. Essentially, we're just going to do the same thing. So we used already degree 2 equations of P1 going to P2. What if we do it here? So let's say we have something like X, Y, Z, and I want to map this to X squared, Y squared, Z squared, XY, YZ, XZ. Luckily, I again have 6 coordinates, so this really maps to P5. This is actually called the Veronese embedding. And the image is called the Veronese surface. For that reason, I'm going to denote it by T. Not for that reason. I'm just going to denote it by T because that's S, and the companion letter of S is T to me. Okay. So how is this related to that? Well, again, this is a degree 4 surface. I mean, it might not look like that, but it is a degree 4 surface. And again, if you take a general hyperplane or just any hyperplane, well, general hyperplane. So it was also here, a general. And by general hyperplane, I mean a hyperplane in general position. So it's not special to our equations in any way. So if I take a general hyperplane, so the thing is, once you believe that this is a degree 4 surface, then it tells us that the intersection will be a degree 4 curve. And by this coordinate description, it's relatively easy to see that that degree 4 curve is going to be a rational curve. So rational curve means isomorphic to P1. So T intersect H is also a rational quartic curve. So now, what do we get here? Let's see. Oh, I should have used the movable one. Okay. Okay, temporarily, I'm going to cover this. If we need it, I will uncover it. I would get in trouble if my board work was evaluated here, because actually I want to use what's behind this board. So hopefully you remember that. But what do we have here? So what we have is that, what is this S? So this S, so this is in P5. Now, well, fortunately, I want to use this too. So replace that X with S and N with 5. If I take S here and then take the projective cone over that, then S is exhibited as the projective cone over S intersected with the hyperplane at infinity. And then if I take the same projective cone and intersect it with a hyperplane through the vertex, then what I get here, well, I didn't write it here, but maybe I can correct that. We did discuss it, that this intersection here is X intersected with A0. And so this yellow guy, this is also the projective cone over X intersected with A0. Is that good? So what that gives us here is that this intersection is the projective cone over S intersected with A0. Okay, now let's do the same for T. It's really exactly the same. So I'll just copy this. So T is the projective cone over that T intersected with H infinity. And then the projective cone over T intersect H0 is the projective cone over T intersected with H0. So now, if we peek behind this, we have here that hyperplane sections of one thing are deformation equivalent. So that means that I can deform S to this and T to this. But S intersect H0 and T intersect H0 are both isomorphic to a rational quartic curve. So these two are actually isomorphic. So I can deform S, which is isomorphic to P1 cross P1, into this cone. And I can deform P2, which is isomorphic to T, to the same cone. So via this cone, I can deform P2 to P1 cross P1 or vice versa. So as soon as we allow just a tiny singularity, so this is actually a very mild singularity. If those words mean anything to you, this is a KLT singularity. So it's sort of as mild as it gets in higher dimensional geometry. So if you allow that, then P2 can be deformed into P1 cross P1. Are there any questions about that?
You see this, I mean, in terms of cells, you've got on one hand, you've got a 4-cell, two cells, and a 0 cell, and the other one, you've got a 0 cell, 2 cells.
Yes, actually,
4 cell.
yes, thank you. I actually meant to say that. I just, when we were there, I forgot. So when I was talking about cohomology classes, so if you describe these as CW complexes, then that actually tells you what the cohomology classes are. So it's sort of the same thing. So with cells, it may be more.
Deformation.
Oh, this deformation. Not really. Well,
in the middle.
Exactly. So actually, okay. So this is actually a very good point. So if you want to see this with cells, it tells you that. So one of these have more cells than the other, which is I think it's this one. So when you deform that into that cone, you have to crush some of those cells. But in the other deformation, you don't. So actually, this is the next step. So that's where I asked if there are any questions, because the next thing would be to kind of analyze what this really means. And let's see what that means. Okay. Doing pretty well with my slides or my notes, but my notebook doesn't want to respond. Okay, so so we saw that these two cannot be deformed into each other as complex manifolds. They're not homeomorphic, and there's actually even an algebraic reason. So I didn't want to lead with that, but for an algebraic geometer, the reason that these two cannot be deformed is that there are some fundamental invariants that these two manifolds do not share. And actually, let me backtrack for a second. So manifolds have something called the Chern class, right? Or more generally, if you have any line bundle, then any line bundle has the Chern class. But for a manifold, we usually take the tangent bundle, and then the determinant of the tangent bundle is a line bundle that has a Chern class, and we look at that. And if we have a deformation of complex manifolds, then the Chern classes should go to Chern classes. And now the trouble is that if you look at Chern classes, so if I look at the Chern class of P2, I'm in certain, so depending on your favorite representation of how you think of Chern classes, but this lives on P2, this lives in a group that's Z, that's isomorphic to Z, and this C1 is either 3 or -3, depending on how you choose the determinant of that. But for sure, the square of this is 9, the cup product with itself. If you do the same here, you get P1 cross P1. And the square of this is 8. So again, that's another reason. And probably you can get this with cells as well. That's another reason why they shouldn't deform to each other. And actually, this is kind of a trouble in the algebraic world. And I'm saying that in contrast that in the algebraic world, we're okay with singularity. Maybe you're okay in analytic world too, but I do want to allow singularities. But this is a problem because there's something called the Hilbert polynomial. And so the Hilbert polynomial, I don't want to give you the definition because if you haven't heard of the Hilbert polynomial, it's not illuminating. The point is that this is an invariant of a projective subvariety of a projective space. And this is constant in families. So this is a very basic result about Hilbert polynomials. That's one of the reasons that we like Hilbert polynomial. That if I have a deformation, then it remains constant. And this number, the square of the Chern class, is a coefficient of the Hilbert polynomial. So if I have a family, then the Hilbert polynomial should be constant. But those two guys are their Hilbert polynomial is different. And now we're actually in trouble. It seems like there's a contradiction in math because this fact does not require the fibers to be manifold. This works for any arbitrary algebraic variety, projective algebraic varieties. So it looks like this construction kind of broke the Hilbert polynomial. Anyone has any guess why that's not the case? Obviously, I'm cheating a little bit, but not too much. Here's the cheat. So when we say Hilbert polynomial is constant in families, that's kind of a simplification of the actual statement. The actual statement is the following. If I have a family, and if I have a line bundle on X, then the Hilbert polynomial of the restriction of this line bundle on the fibers is constant. Now, obviously, when I say Chern class, that really corresponds to the Chern class of the determinant of the tangent bundle, or as algebraic geometers like to do, it's the inverse of that, which is really not a big difference. But so what we're talking about is the Hilbert polynomial of the fibers, of the canonical bundle of the fibers. And now here lies the issue why this actually doesn't break math, that when I allow this cone, its canonical class is actually not a line bundle. And what that means, even worse, in one of those families, actually, right. So in one of those families, the relative, okay, sorry, let me backtrack for a second. So I want the Hilbert polynomial of this guy. So what would be the obvious choice for the line bundle, the global line bundle? The global line bundle would have to be the relative omega. So you take the relative tangent bundle, take the determinant of that, and take the dual of that. That's that. So this would be the obvious choice. But if the fibers don't necessarily have a line bundle for that sheaf, then the relative is also not necessarily a line bundle. That itself would not be actually a problem, because all of these guys, including those, so omega x may not be a line bundle, but they are actually a Q-line bundle. But they are Q-line bundles. So actually, instead of looking at the Hilbert polynomial omega, I could look at the power. So what does Q-line bundle mean? That means that if I take some tensor power and then take the double dual of that, then this is a line bundle. So I could take the Hilbert, that's a line bundle. So now each fiber omega xb is a line bundle, but when I take a power, I can compute the coefficients of the Hilbert polynomial from the coefficients of the Hilbert polynomial here, and they will still be different. So it still seems to be breaking things. But here's the thing, which is actually the first step in higher dimensional moduli or moduli theory of higher dimensional varieties of general type. The problem is that even though each fiber, the canonical sheaf is a Q-line bundle, so some power, some reflexive power is a line bundle, the same is not necessarily true for the family. So this guy, in one of those cases, and I'll let you guess which one, the relative canonical sheaf is not a Q-line bundle. So no matter what you do, when you restrict whatever power you have, it cannot restrict to this because this is a line bundle, and a non-line bundle cannot restrict to a line bundle on a fiber of a family. So the point is that there's no break, because in one of these cases, we don't have this restriction requirement. So it's not a problem that the Hilbert polynomial doesn't break. And it foreshadows, or it tells us what the first step in moduli theory should be, namely, we want to require that this guy is actually a Q-line bundle. Not just that it exists, but it's a Q-line bundle. And it is a relatively easy thing to prove that if this is a Q-line bundle, then the appropriate power restricts correctly to the, the appropriate reflexive power restricts to the reflexive power here. And then that means that this Hilbert polynomial theorem kicks in, so the Hilbert polynomial will have to be constant, so everything is fine. Any guesses which one is the culprit? Which one doesn't work? Anyone? No, it's the other one.
Yeah.
So, so the reason is actually that this is a product, and it was embedded asymmetrically. So its tangent bundle is unbalanced. But if you have something coming from the global embedding, then it would have to be symmetric, because the restriction of the hyperplane actually, sorry, I'm not sure if I said the right words. The embedding is unbalanced, so the hyperplane restricts to one on one and 2 times the other, but the canonical class is symmetric. It's 2, 2, or -2, -2. So in order for this to work, the restriction of the hyperplane class has to be comparable to the canonical class. So basically, you can get a similar example from any product where the hyperplane is not comparable to the canonical. So it wouldn't not have worked for the first embedding, because that was symmetric in the 2 cases. So this tells us that this deformation doesn't have that this would be a Q-line bundle. And as the first requirement for a stable family in higher dimensions is exactly that, we require that the relative omega is a Q-line bundle. So that's actually not an allowable deformation, which is good, because even though we go through something singular, we still wouldn't want P1 cross P1 and P to be in the same moduli. That, if both of these were allowed, then they would end up same connected component of some moduli space, and that wouldn't be very good. So maybe this is a good place to stop. Thank you.
for any field marine, but we have this configuration, but like if we just try to deform one to another, it's not possible, but if we allow singularities,
Oh, no. So this is kind of, well, do you mean for these particular embeddings? So, okay, so
but I mean, could you give? I mean, could you say for this particular embedding, and if it works for any other?
right. So for this particular embedding, the base field essentially doesn't matter. So you get into the problem. It's a well, okay. Well, it does matter a little bit because so if you have a non-closed field, it's possible that this intersection would not agree with the other intersection because you don't have all. So depending on how you choose that field. So if you allow algebraically closed fields, then everything is fine. If it's not algebraically closed, then the problem is that you get this S intersect H and T intersect H could be non-isomorphic over that field, but isomorphic over the algebraic closure. As for other objects, I think it's so okay. I'm not going to theorize on what you might have asked. You can ask more if you want. Does this answer your question, or?
In the sense, is it possible to make a similar construction in like if it's not algebraic field R2 or something?
Yes. So basically, the key point of the construction was that if you take so here the key part was that the intersection. So you have an embedding of your object into some projective space. You intersect that with a hyperplane. If you have another object, you embed it into the same projective space and intersect it with the hyperplane, and the two intersections are isomorphic, then the construction works. So it could be arbitrary two. So what this says is that if you have two complex manifolds and for some embedding, they have isomorphic hyperplane sections, then the two manifolds can be deformed into each other through something singular. So that's the key point of the construction.
But they should be complex.
Oh, no. Okay, sorry, I was in that mind, but that doesn't matter. As long as you get the isomorphism. So I just said complex because it would be harder. So I haven't checked whether if you do this over the reals, whether these intersections would actually be isomorphic. I'm not sure. It could be because these are not very high degree, the embedding polynomials are relatively low degree. So it's possible that this already works over the reals, but I just haven't checked. But as long as you have the fact that the two intersections are isomorphic over that field, then it works.
Thank you.
Other questions?
Is it possible somehow to visualize this deformation? But if two embeddings would be hard, so probably the answer is no. Usually there is an invariant definition of these manifolds. It can be varieties. So maybe make a
I'm not sure what you're asking, sorry. I'll visualize. I can't say it's not possible. I usually, so my specialty is higher dimensional geometry. And when I teach about that, usually the first thing I tell my students is don't try to visualize. Because it's, if you think about it already, can you visualize a projective plane over C? That's already a 4-dimensional thing, right? So then you embed it into P5, which is in our mind is a 10-dimensional. So you know, topologically, it's a 10-dimensional.
I see the problem with sovereignty,
Yeah.
and over.
Although if we go with real, but even that, you know, even if you roll with reals, I don't claim that I can visualize anything higher than 3 dimensions. I almost said 4, but you know, I have given like lectures to high school students, and I try to explain higher dimensions. And you know, I said dimensions are degrees of freedom. You know, you can move this way, you can move this way, you can move this way, or you can move this way. Now you don't see my arm because I pointed out from this free space. It, you know, it disappeared to most of you, but you know, that's how far my imagination goes about higher dimensions. I can tell you this: if you try to visualize and turn that into a mathematical argument, there's a very high chance that you will make a mistake. So I know a book where there's an example about some construction, higher dimensional construction, where they did make this mistake that they're looking at, you know, something like 4-dimensional objects in an 8-dimensional space, and then they look at the intersection, and as it's described, they actually don't intersect. But you know, if you're thinking of, you know, even if can you imagine 2 planes that only intersect in 1 point? Of course, yeah, it looks like this. But can you really? Because if I think of two planes, they actually intersect in a line. My mind lives in a 3-dimensional space, my visual mind. So, you know, there are things that I think of when I think of higher dimensions, but as a principle, I never go by that. I always try to find an argument. And so far, I think, you know, it could help you get some intuition, but never a proof, I think. Prove me wrong, please. It's no, I would love someone to actually see these higher dimensions. It just I'm not that person. So there are, I mean, there are deformations. It's just one of the deformations is sort of a little bit weird or wacky. I'm not sorry. I'm not sure what you're getting at. Well, so the problem with equations is that you know, already for, you know, if you take a high genus curve in some high genus space, it's really hard to write down equations. So it's I mean, writing down equations tend to be low-degree equations that we understand. So I mean, there are equations, of course, because I can show it to you that there's a closed subset of sub-projective space, but writing down explicit equations, that's pretty hard. Although I think in this particular case, since you have particular parameterization, it would be, I mean, this can be turned into equation. So you can, you know, the H infinity is given by the embedding. And so you just have to choose this H0 somewhat generally. So I think from this construction, for these particular families, you can write down equations. But I don't know if that would help. I think Abiyankar was the last person who looked at an equation and could tell you something about it. And he was actually amazing. He wrote down an equation with 9 variables with seemingly random coefficients and would say several properties. Oh, this has this, but I haven't had anyone since then. So, do you think equations would help? Okay. Well, what might help is if you figure out the degree of those equations, right? And that you can. So, you know, you can see the equations here. I mean, these equations don't actually tell you the degree of the surface, because this is a quartic surface, and the equations here are degree 3. But still, you know, you could figure out. For example, I'm pretty sure you could relatively easily find the lowest degree equations that give you these families, and just from that degree, you could conclude something. If there's 2 more minutes, I would add something that's a very algebraic geometric thing, but might be interesting to some people. So a potential question that you could ask, which I didn't really get to, but so when we do moduli theory, when we talk about MG, we usually talk about when someone says MG, they usually mean that G is at least 2, right? So it's usually high genus curves. So the analog that we want to construct corresponds to surfaces or higher dimensional varieties of general type. So moduli theory of varieties of general type. The book that you mentioned is called Families of Varieties of General Type. One thing that you could have pointed out, these guys are not general type. They're very far from being general type. But an interesting aspect is that the issue here is near 1 point. So the only thing where the whole trouble happens is the vertex of that cone. So it's a very, very local thing. So it actually is not that important that it's over P2. There is a construction called a branched covering that could change this. So the same situation can be obtained where the fibers will be actually varieties of general type. But locally analytically, and this is really analytic, not algebraically, locally analytically, the problem point will look the same, but only because every manifold locally analytically is the same as P2 or any other manifold of the same dimension, right? And the construction is that what you can do is, and this works for any complex manifold, you take a complex manifold and take a general hyperplane section of a power of a line bundle, and essentially taking a root of that section. It's the classic thing, but how Riemann discovered Riemann surfaces. You know, when you take a root of a complex number or a complex function, then if you go around the origin, then you have some monodromy. So you actually have to be on a different sheet until you actually get to you have to go around that many times as the root. Same thing, very generally, you can do it with a defining equation of an arbitrary hyperplane or hypersurface section. So you get a branched covering of the original, and that translates to a branched covering of this P2. And the general branched covering of P2 or anything will be of general type if it's high enough degree and general enough. So it ends up being of general type, but locally the computation is the same, the problem is the same. And so this actually informs our understanding of moduli theory of varieties of general type. And this maybe comes back to your question about the equations. In this case, I can write down equations. For that covering case, it would be much harder because then I would have to take roots of those equations. And if I have many, then I don't even want to try to do that. Thank you for the additional